Hi, I'm Seungmyeong Yoon at KASI, and I'm a graduate student at Kyung University. Today I'm going to talk about the IGRINS survey of young stellar objects. First, I'll give a short description of star formation. At the beginning of star formation, giant molecular clouds fall into the cores by gravitational collapse. The material surrounding cores generates circumstellar disks. The envelopes accrete onto the disk, lose their angular momentum, and finally accrete onto the protostar. That's when outflows eject a part of mass from the protostar. As the time passes, the outflows from protostar and circumstellar disks further develop, and envelope gradually disappear. When protostars are young, most fluxes come from IR and sub-millimeter wavelengths. And then, when envelopes finally disappear, protoplanetary disks remain, but protostars still accrete through the circumstellar disks. So at this phase and then when envelope finally disappears, protoplanetary disks remain, and we are able to see the young stellar object through visible light. Then the mass of accretion of YSO approaches the end, and planets and debris disk remain. It is essential for protostars to accrete the mass from the circumstellar disks. Envelopes that extend from hundreds to thousands AU scales accrete onto the disk and move inward. The innermost region of the disk is channeled to protostars by magnetic fields, which mediate mass accretion onto the star. The inner region of the disk consists of the gas within 1 AU in which terrestrial planets form. Therefore, it is important to investigate the physical phenomena and chemical properties associated with the planet and star formation. However, it is difficult to observe inner region directly due to the spatial resolution limit. So we would like to observe the YSOs with high-resolution spectroscopy to resolve them in velocity component. IGRINS is a proper instrument for our purpose. The near-infrared light provided by IGRINS is able to uncover protostars and protoplanetary disks which are extinct in visible light. Also, it is efficient to observe sources since IGRINS cover H and K bands simultaneously. The high-resolution 45,000 can resolve the light profiles that distinguish the kinematics of the system. The difference in resolution is remarkable compared to specs of IRF. So our total sample has 90A, which consists of 45 class 1 sources, 16 class 2, 9 class 3, 17 FEORs, 8 Hurwig AB, and 3 massive YSOs. The spectra shows different features by object types. As you can see from the C Overton band spectra, class 1 sources have emission and absorption spectra in CO, and some have broadened line features, while class 2 and 3 have only absorption spectra. It indicates that class 1 sources have a higher accretion rate by which optically thin disk atmosphere is heated. The emission spectra also can be seen in some Hurwig AB star and FEORs. The absorption spectra in class 2 and 3 sources are regarded as photospheric features. IGRINS spectra shows various atomic and molecular lines in H and K band. The iron 2,4 line and H2 lines in emission in H appears in H band, while K band spectra shows hydrogen recombination line and H2 lines in emission, together with atomic and molecular lines in absorption. Each line arises from different physical environment. First, iron 2,4 line and hydrogen molecular lines mostly arise from jets and outflows or circumstellar disks. The emission lines of iron 2 and H2 can be seen in early phase protostars, Especially in the case of iron 2 line, it primarily appears in class 1 sources. Iron 2 line has several velocity components in which high and low velocity components appear separately by jets and outflows. On the other hand, H2 emission has low velocity components compared to the iron line, which indicates that H2 emission arises from a different area from iron 2 lines. The iron 2 lines is rare in class 2 sources, which generally shows H2 emission only. It indicates that jets and outflows have been developed properly at early phase protostars. H2 emission also have several velocity components, which indicates that these arise from different places. We can fit the line and estimate temperature density, and we can infer the mechanism of the line emission via a rotational diagram. The protostars accrete material along magnetic field channeled to inner disks, which emit strong energies exciting surrounding gas. From this, hydrogen recombination lines, including bracket gamma line, arise. From the bracket gamma fluxes, we can estimate the mass accretion rate of YSOs. Observed hydrogen line shows different fluxes by mass accretion rate of protostars. So if we get a relation between accretion luminosity and bracket gamma luminosity, it will be realized that they have a linear relation on log space. Hence, the bracket gamma line plays a role in estimating the mass accretion rate of YSOs. Also, bracket gamma line have various line profiles which are affected by outflows such as disk winds as well as magnetospheric accretion. Gas in the inner disk is lifted from the disk atmosphere by X-wind or disk wind and accelerate along magnetic fields affecting the bracket gamma line profile. As you see in the figure, we can infer the geometry and physical properties between the protostar and inner disk through the bracket gamma line profile. Also, the near-infrared spectra of YSOs show various atomic and molecular absorption lines. In general, absorption spectra arise from the photostellar photosphere, for which physical properties such as temperature, surface gravity, magnetic field rotational velocity, and veiling lead to spectral characteristics. The high-resolution IGRINS spectra are able to show absorption features which have been identified, and the physical properties of YSO can be derived from comparing it with stellar atmospheric models. On the other hand, in some YSOs, the inner disk atmosphere heated by stellar radiation at a high accretion rate, which generated emission in atomic and molecular species. In this case, we are able to estimate the physical properties of the inner disk. At higher accretion rates, some YSOs shows the emission spectra in C overtone bands, which shows various line profiles by physical properties of the disk. And we are able to estimate the temperature density geometry and kinematics of disk, comparing it to disk model. Next is I'm going to talk about the spectral characteristics of episodic accretion in YSOs. The mass accretion of YSO is variable over time due to the low mass accretion of the disk compared to the envelope accretion. The mass of the disk is fired up gradually, and occasionally, if it is dumped onto the star, brightness increases by several magnitudes. We call these objects as FEORightness objects, in short, FEORs. Outbursting protostars have very hot disk midplane around 10,000 K, which fluxes overwhelming the protostar's luminosity. The radiation from the disk is observed in the disk atmosphere, which produce absorption spectra. The FEOR's spectra observed with IGRINS shows broadened line profiles, which are consistent with the disk models. Such occlusion bars are often found in class 2 sources, which have a lack of envelopes. However, protostars at earlier phase are surrounded by envelope, so it is difficult to detect outbursts. But one of our class 1 samples shows different line profiles from other class 1 sources. It shows broadened line profiles that are consistent with the FeO1 spectra. However, any outbursts were not detected, so we investigate line profiles to determine the source physical state. There are two mechanisms that broaden line profiles. One is the rotation of the protostellar photosphere, and another is the rotation of the disk undergoing the occlusion burst, which produces a double-peaked or boxy profile. We examine the spectra by comparing that with the template spectra compared with each kinematics. As a result, the protostar spectra have shown a spectral type of M-dwarf, and the line profiles are consistent with the template spectra compared with disk rotation velocity of about 40 km per sec. So we conclude that this source have been undergone on occlusion burst. We expect more protostars that shows the spectral features of occlusion burst exist, and we continue observations of young protostars. Also, the high resolution of IGRINS enable us to examine the FeO1 spectra in detail. We found that FeO1 spectra are similar to those of brown dwarf stars or late-type dwarfs. We will continue this analysis to study physical and chemical properties of inner gaseous disk. And we have conducted monitoring observations at infrared sub-millimeter wavelengths to detect variability in YSOs. We use JCMT at 450 and 850 microns to investigate thermal variability in YSOs. And we use NeoWise for sky survey to find the variability. We found several YSOs having variability, and we implemented our observations to examine physical states of YSOs. Our CASI team arranged the variable YSOs and proposed IGRINS observations to Gemini South to study physical properties of protostar and circumstellar disks. This is a summary, and thank you for listening.
Okay, questions from the audience? Thanks for the talk. Questions? No? Slack?
No, nothing.
Nothing? No? Could you please come back to the slide a couple of times before? That's one. No, the next one. Yes. Yeah. You have there are different features in the relative flux and the velocity plot. I would like to ask you, because I'm not an expert in this term, which is the difference because of the two features in that plot?
This one?
Yes.
Yeah. This is
because you have a 10 kilometers per second of difference. It's because of rotation, or it's because of what?
This is the solar rotation of 60 kilometers per second, and these are disk rotation of 40 kilometers.
It's because of a disk.
Yeah, it's a template spectra and comparable with the models.
Okay.
And these are sources spectra.
I understand now. Yeah. Thank you. Is there any question in the audience? No? In Slack? No? Okay. Thanks again. Okay.